else do we want to know?
Their composition.
Their composition, and what else? Proportions. Proportions in what sense?
Just the size.
Yeah, the size. Like the dimensions of the atom, the size, the weight, that kind of stuff. Yeah. You know what we call the size, the weight, and that kind of stuff? We all group that into one big category. What is that category called? If you talk about mass and the size, how heavy it is, density, what do you call those things? The charges? We want to know the charges.
The properties.
Properties, yes. So we want to know the composition, the structure, and the properties of atoms. And then we can get a better understanding of atoms. And so this is what chemists are going to be looking at. And so that's not all going to be covered in this chapter. You know, after we finish this chapter, there's still more stuff left to try to sort through. But this is just the first part of the chapter. And so the learning objectives are here. You can take a look at those. But the chapter starts off with Dalton's atomic theory. Dalton's atomic theory, this is something you don't need to memorize. You know, a lot of these things are just kind of intuitive once you believe in atoms. Do you believe in atoms? Yeah. Well, during Dalton's time, there are a lot of people who didn't believe in atoms because nobody had ever seen an atom. If you see an atom, then you can be a believer. It's like, there's a lot of alien stuff going on right now. And so, do you believe in aliens? Well, show me an alien and then I'll believe in an alien. But have you seen an alien? So what, you have? All right. Then, what we want is we want some proof, right? We want some observations, and with detailed observations would be good. And so,
Was atomic theory derived from, was it derived from theory or no?
No. Atomic theory was not derived from theory. Atomic theory was derived from observations, exactly. And these observations, it's like, where does this whole extraterrestrial stuff come from? Well, some people saw observations. They saw observations of what they call unidentified aerial phenomena now, UAPs. Have you heard of that? And then people have different hypotheses. Some people hypothesize that these are just glitches in the electronics, or some kind of a reflection. So these aren't real. These are artifacts. Artifacts are things that give the illusion that they're real. So that's one of the hypotheses. Another hypothesis is these are, the way they move, they are counter to anything that's been observed before. And so there must be something else to them. And so this is the same kind of thing. But eventually those observations add up to something like this, and there's widespread adoptance of atomic theory, even though they haven't observed atoms. Nowadays, we observe atoms. People can manipulate single atoms. People can take images of single atoms. There's no dispute now. And so if there are aliens and you can meet the aliens, then there would be no dispute, correct? But during Dalton's time, this is how science progresses. So we're seeing a kind of a repeat here with the whole maybe it is aliens, maybe it's not aliens. You got to do is you can take the observations, see how they stack up.
Why do you call them atoms?
I think it came from much earlier times, like the ancient, some of the ancient civilizations came up. Dalton wasn't the first to propose atoms. Atoms were proposed like 3,000 years ago or something like that, or 2,000, something well before Dalton. The only thing Dalton did was he put it together as a theory. The idea of atoms have been around for long. Who was it? Democles or one of those. And there are other civilizations who have proposed atoms. It's just putting it together with the observations to back it up. What observations did Dalton have to back it up? This was like, this is the same thing when I was talking about the elixir of life and the philosopher's stone. What evidence do you have that there's an elixir of life out there? And so that brought this, Dalton brought it more to that realm of observable science. And there are people, there are mix, they're a mix of like alchemists and a mix of like scientists who are looking at the aliens, the whole alien stuff. Like the Ari Loeb at Harvard, you look at him, he's one of those who thinks that these are outside of our solar system, the origin of some of these objects, and that could represent alien technology. Whereas then there are others who, like there's another person who said he went to MIT and Caltech and then worked at Area 51 and S1, but you hear about element 115, and then you go, it's hard because that would counter the behavior of that particular element, and the element's already been observed. So, there are different people proposing different things, but eventually it'll sort out, and we'll see. But let's take a look at Dalton's atomic theory here. Each element is made up of individual particles called atoms. Atoms are indivisible, meaning atoms are indivisible. Is that really correct now? I mean, can you break apart atoms? Well, in one sense, they're indivisible, because if you try to break them up into smaller pieces, they're no longer atoms, right? But they are divisible in the sense that you can break them up into what we call subatomic particles. Atoms are comprised of just three things, protons, neutrons, and electrons. They can be broken up into protons, neutrons, and electrons, but they'll no longer behave like atoms. All atoms of one element are identical in every respect. So if you have hydrogen atoms, they're all identical, but it turns out that's not correct anymore. Hydrogen has two that are common. There's one hydrogen that's about twice as heavy as another hydrogen. And so have you ever heard of heavy water? Heavy water? Do you know all water molecules aren't the same? There are some that are heavier and some that are lighter. And so, it's because some atoms are heavier and some atoms are lighter, but they're still hydrogen. And so you can't tell the difference. When you drink water, you can't tell if one water is heavier than the other. You're just all similar in that respect. And so this is not true anymore. So this is a case where the theory, yes, although widely accepted, had to be modified when new observations came that countered the theory. And so between fact and theory, fact always wins. And so point 3 here is no longer valid. All right, what's the next point? Atoms of one element are different from atoms of any other element. That is true. So a hydrogen atom behaves very differently than a helium. If you try to burn helium, it just doesn't burn. But if you try to burn hydrogen, no problem. Hydrogen is very combustible. It's very easy to burn. And so that's one of the property differences between hydrogen and helium. We want to understand the properties. So what we need to dig into is what? If I want to understand why hydrogen and helium have different properties, then I need to dig into what? The structure and composition, because the structure and composition of hydrogen must be different than the structure and composition of helium. And so that's what we need to figure out, how they're different. Atoms of one element combine with atoms of other elements to form chemical compounds. That's fine. Chemical compounds and elements are what we call pure substances. They have fixed composition and fixed properties versus mixtures. When we take a look at matter, matter can be divided into three things, right? mixtures, and then pure. And the pure are subdivided into two. So this is where I get three. That could be an element, a compound, or a mixture. That's all we're going to have. That's all we're going to have that we're primarily interested in. But of course, like other things, we can break atoms apart into subatomic particles. So there are subatomic particles, but that's more the realm of nuclear chemists, nuclear physicists than chemists. So this you don't have to. Here's a pictorial representation of Dalton's atomic theory. An element is made up of atoms. All atoms of a given element are identical. This second part is no longer true. And so when we look at the atoms, they all look the same. Yeah. Atoms cannot be created or destroyed. Is that true, or is it still true today? Now we have to separate. In chemical reactions, atoms cannot be created or destroyed. That's what gives us the conservation of mass. But during Dalton's times, he wasn't aware of nuclear reactions. In nuclear reactions, like uranium is unstable and breaks apart into smaller pieces. And the smaller pieces are other atoms, and essentially other atoms. And so in chemical reactions, atoms cannot be created or destroyed. And so we can keep this in chemical reactions. Maybe if we just add that. In physical processes, nothing happens. And so we're looking in chemical processes. But of course, nuclear is different.
If I'm an exam, it asks us a question like, can atoms be broken apart? Do we answer according to the theory or according to what we know now?
According to what we know now, yeah. When we say broken apart, things can be broken apart into subatomic particles. What this is saying that, I guess you could. Well, we don't really have to worry about this too much. In chemical, what I would do is I would qualify it though. I would say in chemical reactions, then this is true. But even in chemical reactions, a small bit of the atom is lost when energy, a small bit of the mass of the atom is converted to energy. This is this equation. Let me write this equation here. Nuclear, we have this equation, E equals mc squared. This is Einstein's famous equation. Einstein didn't win the Nobel Prize for this equation. He won the Nobel Prize for something else. But this equation tells us that when there's an energy change, the energy change comes from the mass change. C is the speed of light, and that's a constant. So C is a constant squared. And what this is referring to is that a little bit of the mass is converted into energy, or some energy can be converted into mass. In chemical reactions, the energies that we're looking at are so small, they're so minuscule, the energies, delta E, that the mass changes are not measurable with our instruments. The mass changes are so small. In nuclear reactions, the energies are huge, so delta E is big, and therefore the mass changes are actually detectable, so measurable. All atoms of any given element have the same properties. Now that's true. I told you that some hydrogens are heavier than others, and the same thing goes with oxygen, but they all have the same chemical properties. Now one of the physical properties that will be different will be the density. So if you have heavy water, it's going to be more dense than light water. Uh-huh. No, hard water is totally different. Hard water comes from the minerals that are dissolved in it. This heavy water is different than this. In geology, this is important for geologists because geologists are interested in what's called fractionation. Fractionation is the heavier stuff sinks to the bottom, the lighter stuff rises. Not just geologists, but chemists are too. So, for example, we have two types of ozone. We have the ozone that comes from pollution, like diesel and electronics pollution. And then a lot of air cleaners. There a lot of air cleaners that use ozone to try to destroy um, things in air. Oh, but if the ozone levels get too high, it's bad. And so there's been some recent studies. They changed. I think the EPA's changed the whole regulations behind ozone air purifiers. You might look into it if you have one of those. But they're around. But the ozone that's produced from pollution versus the ozone that's up in the atmosphere, wherever, compositionally is different. It's the same thing as pure oxygen, but there's lighter oxygen atoms and heavier oxygen atoms. The ozone that's produced down here is richer and heavier ones than the ozone that's produced up there. The ozone that's produced up there is richer in the lighter ones. And so if you take samples, you can determine where it came from. And so geologists do this all the time. They look at isotopic fractionation, and chemists do this too, environmental, if you want to trace it. There are other things. All atoms aren't identical. So a lot of biochemists, I was working on a floor with a biochemistry group. In this biochemistry group, they used radioactive phosphorus all the time. They would put radioactive phosphorus in place of normal phosphorus, and then they could just use a little Geiger counter to detect. They want to find where the radioactive phosphorus ends up in your biological systems. And with this phosphorus, we're phosphorus-based life form versus something like arsenic-based. And so that's called radioactive tagging. And so in that case, they're phosphorus atoms. They're going to have the chemical properties of phosphorus, but they're different. And so when we say same properties, we'll just say chemical properties. But mass and density might be different. Mass. The difference in density comes from this. All hydrogen atoms, because atoms are made up of protons, neutrons, and electrons, all hydrogen atoms have the same number of protons, but they don't all have the same number of neutrons. Now, neutrons aren't going to affect the chemical properties, but they will affect the mass. So they should have the same chemical properties, but mass and density might differ. And the chemical properties, it depends, because some chemical properties will depend on how fast it moves. So if something's heavier, it tends to move slower because of inertia. Atoms of different elements may combine in a ratio of small whole numbers. You know what we call this? Called this the law of what? Yes. And so this is a little pictorial representation of Dalton's. A lot of this is kind of intuitive. All right, so let's go on to the law of multiple proportions. So here is an example, carbon monoxide, carbon dioxide, but are we going to have anything in between? No, so this is one of the arguments for atoms versus infinitely divisible matter. If you have infinitely divisible matter, then we can have anything in between. We should be able to have anything in between. Just a little bit more oxygen. And so it's a 1 to 1 or 1 to 2. or whatever, but not something between. This was how do they do this? Well, they back in the back in those times, they were able to analyze these to figure out how many grams of carbon, how many grams of oxygen, and then they see the mass ratio. The mass ratios came out to a 1-to-1 type ratio or 1-to-2 type ratio, and so that's what they did. So atoms are made up of protons, neutrons, electrons, and so the electron. Let's take a look at that. It's a subatomic particle carrying a negative charge. And so the symbol for that is E for electron, and this little minus means a -1 charge. And it has a very small mass. So one thing is electrons are very light. They're not very heavy. If we look at the hydrogen hydrogen and proton, it's about 2,000 times lighter than a proton. And so, it's 1,837 times, but I'm going to round it to 1 sig fig, and we'll just say about 2,000 times lighter than a proton and a neutron. Then protons. Protons have this symbol, P plus, and neutrons. Neutrons have the symbol N with a 0 for neutral. P with the positives for protons, so about 2,000 times lighter. We have the mass of the electron. What is the mass? I'll write it later, but usually what we say, we have different units for the mass, and the mass in grams or kilograms is inconvenient because it's so light. And so we have one more type of unit. The one more type of unit is called the AMU, or just the U. And these are the atomic mass units. If you look at 1 gram, and this number will become more important later, in 1 gram, there are 6.022 times 10 to the 23rd atomic mass units, or U, in 1 gram. And so atomic mass, so if you take a gram and divide it into 6.022 times 10 to the 23rd parts, one of those parts would be 1 atomic mass unit. Now, how much does an electron weigh in atomic mass units? To 1 sig fig, an electron weighs 0.005 U. Roughly. This is to 1 sig fig. We could be more precise and not round it so severely, but it's hard to remember if we have a lot of digits. It's a lot easier to remember if we just have 1 digit. And so 1 electron has a mass about that. This is the mass. Whereas 1 proton mass will be, we're just going to round it to 1. Actually, this one will round to 2 sig figs. 1.0 U will be 2 sig figs. And 1 neutron has a mass of, it's about. These are all about. These aren't exact. 1.0 U. And so proton and neutron are about the same. One's just slightly heavier than the other. An electron is quite a bit lighter. And so the U, atomic mass unit, is convenient, but how is the atomic mass unit defined? Do they have a little tiny piece or of matter locked away, or do they have a little? Maybe they put an electron in bell jars. That way they can weigh it. Do you think you'd be able to weigh that on any kind of balance? No. And so the question comes up is, how is the AMU defined? You know, the easiest would be, let's just call the proton exactly 1 AMU. Why didn't they do that? Because this is on the arbitrary scale. You can define it any way you want. And so if you call a proton exactly, and so how is the AMU defined exactly? With no uncertainty, infinite sig figs. So we'll leave this question open and talk about it later. Come back to it. Anyway, how was the electron discovered? Do you know, have you ever heard of the cathode ray tube? Its discovery is credited to J.J. Thomson. J.J. Thomson did a very famous experiment with the cathode ray tube. Have you ever heard of a CRT? Hmm? You think so? Okay. You know the old television sets and old oscilloscopes and old instruments used to have CRTs. Like if you look at the old movies where they're looking at the display, and there's some like radar display or whatever. Since I was looking at the UFO stuff, those are cathode ray tubes that they use. And cathode rays were mysterious, but eventually somebody figured out, J.J. Thomson figured out what cathode rays are. Do you know what cathode rays are? Cathode rays sound like some kind of, death ray for aliens, something like that. But what cathode rays are just a beam of electrons. Cathode, it's just, we have different, when we're dealing with electricity, we have something called the cathode and the anode. The cathode is what we call the positive, like a battery. You know, the positive thing on the battery is called the cathode. So when you have a battery, you look at the positive terminal, that's the cathode. Do you know what the negative terminal is called on a battery? The negative terminal on a battery is called the anode. And do you know batteries, what the batteries pull electrons through it to make a circuit. And so cathodes are positive and they pull electrons. So what's happening with this beam of electrons is it's like a lightning bolt, but it's a controlled lightning bolt. A lightning bolt is a beam of electrons, so you can call a lightning bolt a cathode ray. But it's a little bit different here, but kind of the same thing. Lightning bolts are more jagged. The cathode ray here is more controlled. Lightning bolt's more jagged because there's a lot more air molecules it can collide with and cause its path to deflect. But in cathode rays, we try to keep a high vacuum. That way these electrons have a free path to travel. And so that's where the name comes from. But essentially, J.J. Thomson figured out that these mysterious cathode rays are actually electrons. And he used the cathode ray tube for this to determine it. So let's see the cathode ray tube. Do we have the cathode ray tube? No. Let me show you the cathode ray tube since we brought up J.J. Thomson here. I'm sorry? There's no anode ray. If you're in physics, when they started discussing electricity, they could have, they weren't sure, right? They weren't sure if the charge carrier were negative or positive. And so in physics, they have it backwards, but, historically it's always been backwards, so they just left it like that and make an explanation that it's the electrons. When you have electricity, what travels? Do you know what travels? The electrons travel. In physics, when you do the calculations, it's always the positive that travel. The protons don't travel, through a wire. It's the electrons that travel. take a look at the cathode ray tube. This is the cathode ray here. The electrons are invisible. The audio
Okay,
doesn't work.
this is a cathode ray tube. What it essentially is, it's a
But what's happening
vacuum
is the electrons
chamber.
are hitting that
There are
white
no
space to
gases
have one of
inside
these
this glass tube.
Otherwise,
The only thing we have are two electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? It does appear as though it's happening to it. It's moving. It's being repelled, isn't it, by the magnet? And we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now at the time that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound?
Hydrogen.
Because hydrogen's the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron.
Were discovered in crafty methods. You can read about those, but those we aren't going to worry about. It's just the discovery of the electron that deemed okay for this particular course. And so we know that the atom is made up of protons, neutrons, and electrons. And so there are two competing models or hypotheses for the structure of an atom. And so if you have protons, neutrons, and electrons, how big are they? How much do they weigh? And how are they structured?
They're smaller than that's for sure.
Yeah, they're smaller. The protons have been measured, the size. The electrons are more tricky. Do you know how big an electron is? We know how much an electron weighs, but do you know how big it is?
Small.
Yeah, it's so small, they call it zero. It has zero size. How can something have zero size?
How do you define that?
How do you define it? And so electrons are very tricky to define. And so more recent physics have defined it in a way that seems to make sense, but we'll talk about that later. You have to realize electrons are weird, and that's what we'll say for right now. So the plum pudding, what they said was the negatively charged electron particles are embedded within positively charged spherical gel. So the positively charged spherical gel is the pudding, and the electrons are the plums. So if you have a bunch of pudding, you put the plums and spread them all around. And so it's kind of heterogeneous, it's kind of homogeneous. It's kind of homogeneous in the sense that Um, it's like a chocolate chip cookie with the chocolate chips all spread out evenly. It turns out that that was disproven. The plum pudding model is no longer considered. Instead, what we have is the nuclear atom model, which is shown here. And the experiment that determined this was done by Rutherford. And so this is the Rutherford gold foil experiment. And what this did was it offered solid evidence for the nuclear atom model. So the plum pudding model was replaced by this. The reason is because what Rutherford did was he took a radioactive atom is stable. And chunks of it are apart. Some of these radioactive atoms are just too big. And these chunks can be what we call alpha particles here. These are different than cathode rays. Cathode rays are electrons. Alpha particles or alpha rays are little chunks of bigger radioactive ones. But these little chunks are atoms themselves. These are atoms of helium. And so alpha particles are atoms of helium, but unlike helium, they're missing parts of the atom. And the helium is very stable. It's fairly unreactive. The people who inhale helium, you got to be careful about inhaling helium because you don't want to. There are, cases of death from, I think, asphyxiation, not enough oxygen. But otherwise, it's not chemically reactive. Helium is pretty stable stuff. The alpha particles aren't. Alpha particles are helium atoms that have lost all of its electrons. So it's very reactive. So alpha particles are some of the most serious form of radiation or radioactive particles in this case. There are two types of radiation. There's light radiation and particle radiation. These are the most dangerous form of particle radiation. And alpha particles can be more dangerous than light radiation, which consists of X-rays and gamma rays. But anyway, these alpha particles are breaking off the radioactive source in all directions. So what they do is a big pinhole here. This is a sled. Or actually for alpha particles. Not only do you get alpha particles, but you can also get gamma radiation, light radiation actually. So you can encapsulate this in lead, put a pinhole here, the alpha particles shoot out like this. And what they do is they shoot out onto this. This is like a fluorescent screen, so this will start to glow when the particles hit it. Just like the electrons also things glow. And what they see is the brightest glow comes straight line, a straight line path with alpha particles. So here's the brightest glow. And then there's some other strikes here. There's a strike here, and then once in a while you have a strike way out here. And so how can you explain this large deflection? We can explain this large deflection. Our alpha particles, we know, are missing electrons, so these are positively charged particles. But what happens if a positive charged particle hits a positive charged particle? Do like charges attract or do like charges repel? They repel. So what's happening here is that a positive and a positive hit. And so that means all the positive charge must be concentrated. Because most of the positive charges went straight through. And so most of the positive charges and alpha particles went straight through, but some were highly deflected by hitting another source of positive charge. This other source of positive charge must be concentrated in what we call the nucleus. And so this changed the way. The plum pudding, the way that scientists visualize the atom, in the plum pudding, the positive charge is spread out over the entire sphere, and the electrons are little crumbs. So we just expect small deflection, positive repulsion. And the electrons would result in attraction. The electrons don't weigh much, so they don't cause much attraction. So what we see is that all the positive charge is concentrated in what we call the nucleus. And one other thing that happens is the mass. This is mostly empty space. So if this is mostly empty space because the alpha particles just go straight through it, then most of the mass must be concentrated in that tiny nucleus as well. And so in the nuclear atom model, we have the nucleus, which contains the positive charge. The positive charge comes from the protons. And so in the nucleus, we have all the protons. And it turns out we have the most of the mass. So all protons and all neutrons are contained there. There's one element, one atom that doesn't have neutrons. That's hydrogen. Hydrogen may or may not have neutrons, but everything else does. And the electrons occupy empty space outside the nucleus. And so when we look at the nucleus, what we need to know is that all the positive charge and nearly all mass. And nearly all the mass is in the nucleus. This is the Rutherford Goldfield experiment. So we have the nuclear model of the atom. Every atom contains a small and extremely dense nucleus. You know, I asked you what the density of gold, or let's say, like the density, what's the density of osmium or iridium, roughly?
29, 28.
That's a little high.
22.
22. Yeah. Do you know what the density of the nucleus is?
30.
No, the density of the nucleus is about 2 tons per cubic centimeter. 2 tons. Yeah, that's impressive. It's phenomenal. Contains the atom's positive charge and nearly all its mass. The major volume of an atom is nearly empty space. Atoms consist mostly of empty space. Mostly empty space. Space outside the nucleus is thinly populated by electrons. These electrons reside. The total charge of electrons balances out the total positive charge. So in other words, this last statement just says that the number of protons is equal to the number of electrons, which doesn't necessarily equal the number of neutrons. The number of neutrons can vary. This is number of protons equals the number of electrons for neutral atoms. Now, if we have a charged atom, we call it an ion. For neutral atoms, ions are different. Ions will have an imbalance. Of protons and neutrons. Not neutrons. Protons and neutrons. That's what causes the charge on ions. There's that imbalance.
I think so. Okay.
You know what 10 to the minus 10 meters is called? No. 10 to the minus 12 meters is a pico. 10, no,
10
no. I didn't make you memorize it because the book is saying it's old now. It's falling out of favor, but you still need to, you probably should have heard of it before because it's still in use. 10, it's not 10 to the minus 10. It's not the prefix. It's this whole thing. 10 to the minus 10 meters. No. Yes. This is defined as this A with a circle on the top. And that was called, what was it called again? Yes. So this is about 1 angstrom. What this is about 10,000 times smaller than nucleus. So if this is 1 angstrom, let's say this is roughly 1 angstrom. This is for hydrogen. This is about the smallest atom. The other ones are going to be bigger. How much bigger, about? Well,
Not too much.
not too much, but a bit bigger. The nucleus is about 10 to the minus 5 angstroms, about 10,000 times. Here they have a 10 to the minus 4 smaller. So let's just say 10 to the minus 4 to 10 to the minus 5. So they have 10 to the minus 14 here. But up here they say 10. They say 10,000 times smaller here, but then they did, 10 to the 4 is 10,000 times, sorry. 10 to the minus 5 would be 100,000 times smaller. Excuse me. 10 to the minus 4. Diameter of the nucleus is about 10,000 times smaller. So it's easier to remember certain numbers. Angstroms is easy to remember. U or AMU is easy to remember. This nucleus is shown 1 centimeter in diameter. So actually, this is bigger than 1 centimeter. I think on the printed page it's 1 centimeter. The diameter of the region occupied by its electrons would be 100 meters. So if this were 1 centimeter, then 100 meters is about 100 yards. And so this would be about 1 football field. And so if the nucleus were 1 centimeter, then the atom would be about 1 football field big. So that's just to give you a perspective on the dimensions there. Okay. Combining results of the experiments with the nuclear atom. Well, this is the Rutherford. So let's just talk about Rutherford. What was the foil again? What's the symbol for gold? So let's say AU foil. But most of the alpha particles were not deflected. They went straight through. That's because it's mostly empty space, right? Atoms are mostly empty space. A fraction of the particles were slightly deflected as they passed close to the nucleus, as you'd expect. Particles near the nucleus are repelled by strong positive electrostatic forces. So that results in a small number of particles on a collision course with the nuclei will repel backwards. It's like trying to bring 2 North Pole on a magnet, on 2 different magnets together. They repel each other. The more you try to force them, the more force of rejection you're met with. And so those are just some. So inside the nucleus, we have the protons and the neutrons. The protons carry a positive charge of +1. Electrons are -1. These were discovered by Rutherford. What else did Rutherford do?
The experiment.
Yeah, the Rutherford gold foil experiment. But Rutherford also discovered the proton using something similar to the cathode ray tube. I think he discovered it using cathode ray tube or something. You could read about this, but you're not responsible for this. If you need to know Rutherford, what was Rutherford known for? Of course, he was known for the proton, but for you, Rutherford was known for the gold foil. Who's known for the electron? J.J. Thomson. Here, you don't need to know this. The neutron was discovered by James Chadwick. We don't need to know that. Neutron is electrically neutral subatomic particle within the nucleus. Its mass is approximately equal to that of a proton, and the symbol is N0. Honestly. Well, this is a repeat of the earlier slide. Let's skip this one. Okay, so let's take a look at, we have things called isotopes. I told you that there's heavier hydrogens and lighter hydrogens, and those are called isotopes of hydrogen. Hydrogens are the same element, but different mass. And the mass is a result of a different number of neutrons. And so same element, but different number of neutrons, which would cause its mass to be different. And so that brings us to this. The atomic number, Z, is the number of protons in an atom of an element. This defines the element. So each element has a number. So for example, if you look at hydrogen, what number is it? On this periodic table, it's a red number, and it's element number 1. So hydrogen, we say Z is equal to 1. Regardless of how heavy or light it is, it has a Z of 1.
You may have like one electron too because elements in this neutral.
Yeah, when it's neutral, it would. But the number of protons varies for hydrogen. And so when we look at hydrogen, there are 3 common, what we call isotopes of hydrogen. Let's take a look at the 3 common isotopes of hydrogen. In nature, we find hydrogen with 1 proton, 0 neutrons, and 1 electron. And then we also find hydrogen with 1 proton, 1 neutron, and 1 electron. And we find hydrogen with 1 proton, 2 neutrons, and 1 electron. So compositionally, they're different, but what defines an element is the number of protons. And so hydrogen, if it has 1 proton, is always hydrogen. If we have 2 protons, it's no longer hydrogen. Do you know if we have 2 protons, what element that is? Helium, is correct. And so 2 protons is the element helium. 1 proton is hydrogen, regardless of how many neutrons it has. And so we have to account for these 3 compositions of hydrogen. Heavy water consists of having these heavier hydrogens and isotopes. Isotopes are 2 or more atoms of the same element that have different masses. So there are 3 isotopes here. 3 common isotopes of hydrogen. Well, one of them is kind of rare, this last one. So let me come to the last one. 2 or more atoms of the same element that have different masses, differing in the number of neutrons identified by the mass number. Well, the mass number is a little different here. The mass number is the total number of protons and neutrons in the nucleus of an atom. So that's what we call A. Z is the number of protons. It's called the number of protons is called the what? Atomic number. N is the number of neutrons, which doesn't get a fancy name like protons. The number of protons has this fancy name, the atomic number. The number of neutrons is not as important because it varies. A is called the mass number, but it's not a mass. A is not equal to the mass. It is equal to the mass number. So what's the difference between a mass number and a mass? The mass is equal to how much it weighs. The mass number is not equal to how much it weighs. Do you know what the mass number is equal to?
Mass number?
Is it?
Isn't that the average of the different isotopes?
No. It could be. We call that the atomic mass. Is the average. Yeah. The mass number is different. The mass number is equal to the number of protons plus the number of neutrons. And since most of the mass is in protons and neutrons, then what that means is that the mass number is approximately equal to the mass. And so we'll just say this is approximately equal to the mass of the isotope. The reason we say it's approximately equal to the mass, we have to be careful because it's in certain units. Do you know about how much a proton weighs? Does 2 sig figs?
0.005.
That's electron.
1.0.
1.0. So a proton weighs about 1.0. How much does a neutron weigh? 1.0. How much does electron weigh? Yes, 2,000 times less. And so what that means is that the electrons don't weigh much. And so if we ignore the electron, then this is about the mass of the isotope, because in AMU, or atomic mass units, this is about how much it weighs in AMU. So what are the mass numbers up here? For the first one, 1 plus 0, that gives us mass number 1. 1 plus 1, mass number is 2, 1 plus 2. And they weigh about that. And so this first hydrogen weighs about 1, the second one about 2, third about 3. Now, that's the composition and something about its weight. And so let's take a look at the nuclear symbol. So we have 3 isotopes of hydrogen. We have, okay, this is the way we say it. So for example, we have hydrogen 1. Hydrogen hyphen 1. Hydrogen 1 has a mass number of 1. It says 1 proton, 0 neutrons. And then we have hydrogen 2. And we have hydrogen 3. Now, there are common names for these. Heavy water was a big deal. You know why people wanted heavy water? People still want heavy water. Do you know why people still want heavy water? They want heavy water for the heavier hydrogen. And do you know what they want to do with the heavier hydrogen? They want to fuse these are nuclear chemists, nuclear physicists. They want to take these hydrogens and fuse them together to get 2 protons to fuse. How do you get 2 protons to fuse together? Do you know? Because what happens when a positive encounters a positive? They repel. Remember Rutherford? Rutherford, they repel. They are going to bounce off each other. However, if you give it enough speed, that is, if the 2 hydrogens are moving so fast that their energy can overcome the repulsion, then the 2 nuclei can come into contact. And if the 2 nuclei come into contact, there is the possibility that they fuse together. And if you get one atom with one proton to fuse together with another atom with one proton, then how many protons would you have? 2 protons, which is what element? Helium. And so the whole reason they want heavy hydrogen is it's easier to get them to fuse together. Mhm. Well, no, not the speed, but it's just the mechanism of how it reacts. And so that's called nuclear fusion.
So the primary helium and hydrogen.
Yes, they're trying to make helium. Do you know there's a big nuclear fusion reactor going on right now? You probably know it. What is it? A big nuclear fusion reactor going on right now is taking hydrogens and fusing them together to make helium, and that's the sun. That's the fusion. So people are very interested in heavy hydrogen because they want to make nuclear fusion happen.
Can you do that with other elements?
Hmm? What's that?
Can you do that with other elements?
Yes. Oh, yeah. They can do that with other elements, but we want to do it with hydrogen because the other elements can often make radioactive, what we call radioactive isotopes, which we don't want. Helium is fairly unreactive. Helium is stable, right? Unless it's missing 2 electrons like alpha particles, but we aren't making alpha particles, we're making helium, which is different. Hmm? What defines radioactive is that it's got an unstable nucleus. You know, so some radioactive elements, like, we have fancy names for these isotopes for hydrogen. Let me talk about the fancy names for these ones. Hydrogen 1 is just called hydrogen, usually. And so, this is just normally called hydrogen. We don't have fancy names for all the isotopes. It's just for these because these have such a history to them. You know, I guess during World War II, did you hear about that secret mission to blow up the heavy water plant in Europe or something like that? Because they're trying to make a fusion bomb, you know, not a fusion power plant. But hydrogen 2 is called deuterium. And hydrogen 3 is called tritium. Now, tritium is radioactive. What makes it radioactive is it's got too many neutrons. If you have too many neutrons in the nucleus, it's out of balance. And so having too many neutrons is not good. Having too few neutrons is not good either. If you have too few neutrons, it's not good, and it becomes. But hydrogen 1 is no problem. It has no neutrons. But for some other elements, they don't have enough neutrons. In nuclear, there's theory for this. And the theory goes like this. The neutrons have something to do with holding the protons together. We don't have any problem with hydrogen because there's only one proton there. But when you get to heavier elements, they have more protons. And protons in the nucleus, let's say we have 2 protons in the nucleus, that's helium. What's holding the 2 protons together? Didn't Rutherford do the gold foil experiment? And based on the observations of that, don't the positive repel the positive? Yes. And so if you have a helium nucleus, how big is a helium nucleus? Yeah, like 10 to the negative 5, 10 to the negative 4 angstroms. 10 to the negative 4. It's tiny. So if you have a tiny nucleus, what's holding the protons together in a tiny nucleus? Well, certainly not electrical forces. I talked about, electrical forces. Electrical forces would say that those 2 protons would repel each other. And so what's holding them? What's holding them together is, well, some people say the neutrons are the glue that holds the protons together. So we need the right amount of glue. Too much glue, too little glue, it's not held together very well. If it's not held together very well, then we call it radioactive. Radioactive is unstable. It's going to break apart. Now, there are other ways it can. We can also fuse other things to it, those are different type of force, and different type of force. Those are called nuclear forces. They have the nuclear the weak nuclear force. Those are the weak nuclear forces that hold the protons together. And then they have the strong nuclear force. It turns out the protons and neutrons are comprised of smaller particles. You know what the smaller particles are called? The nuclear strong forces hold these quarks together. But these quarks we don't care about. All we care about is that the atoms consist of protons, neutrons, and electrons. What you do with those, if you want to break them apart, or people are trying to watch, they have these pools of water underground. They're trying to observe a proton decay and break apart into smaller particles, based on the theory. They've been watching for decades, but I don't think they've observed it yet. But anyway, what we care about are the protons, neutrons, and electrons. Now, this is radioactive here, but for us, we aren't going to concern ourselves with radioactivity, and that type of stuff, because that type of stuff plays by different rules than what we play with. The rules that we play with are coulombs, electrostatic forces, that type of stuff. Nuclear chemists could care less about electrostatic forces. But anyway, let's move on here. So what we're going to do is we're going to detail this. So hydrogen 1 gets this. We write this as this. The number of protons, which is Z, or the atomic number. And so we write Z down here, which is the number of protons, or the atomic number. And then up here we write A. A is the mass number. The mass number is the number of protons plus the number of neutrons. And so we can represent the three compositions of hydrogen like this. The first composition of hydrogen, well, all the hydrogens have the same Z, because that's what defines hydrogen. And so we have these three isotopes of hydrogen. They all have the same number of protons. What's different is their mass number. So the first one has 1 proton, 0 neutrons. So that gets a mass number of 1. The second one is hydrogen 2, which has a mass number of 2. And the third one is hydrogen 3. And so this is hydrogen, deuterium, tritium. And the composition we can get from this tells us the composition of the isotope. So, example, what are the nuclear symbols for carbon-12 and carbon-13? Well, carbon's element number 1. You look at the periodic table, it's element number 6. That means it has 6 protons. All carbon atoms will have 6 protons, but they might not have the same number of neutrons. So carbon-12 is written like this. It has mass number 12. Carbon-13 is written like this. And so let's get the composition for these carbons. What's the composition of carbon-12? How many protons?
6 protons, 6 electrons, 6 neutrons.
Yeah. 12 neutrons? The mass number is 12, but what does the mass number equal?
Oh,
Yeah. So the number of neutrons is 6, because 6 plus 6 gives us 12. How about carbon-13? Yeah, carbon-13 is going to have the same number of protons, 6, same number of electrons, 6, but the number of neutrons will be 7. So 6 plus 7 gives us 13. How about, there's one more here. Have you heard of carbon-14? What do you know about carbon-14? Carbon-14 has one important application. Do you know what it is? It's called radiocarbon, or radiocarbon dating, or radioisotope dating. Carbon-14 is not stable. Do you know what we call carbon-14? Yeah, carbon-14, well, what is its composition? Its composition, how many protons? No. All, whether it's radioactive or not, will have the same number of protons. 6. How many electrons?
6.
6. How many neutrons?
8.
8. and it makes it radioactive. What do you guess if we had 9 neutrons? If we had carbon-15, what would you guess? Stable or radioactive? Radioactive, for sure. Radioactive. How about carbon-11? Carbon-11 is probably, yeah, radioactive, unstable. So those are observations that we have. But this is radioactive carbon here. So let's do some fill in the blanks here. Barium, do you know the symbol for barium? Ba. Oxygen, what's the symbol for oxygen? This one I don't know. But based on the atomic number, what's the symbol? Atomic number is 82. What is element number 82? Pb? Pb is called lead. This one I don't know. We don't have enough information. Oh, over here we do have it. What is this one? Zinc. Which is the symbol Zn and element number. What's element number for barium? 56. Thank you. For oxygen? 8. Okay, how many protons? 56, 8, 82, 30. Okay, now we have to go to the, let's go to the, these. This one, number of neutrons, we don't know because the number of neutrons varies. We need additional information for that. And so let's go to the next box. Mass number. Do we know the mass number? Well, they give us the nuclear symbol, so we should be able to figure it out. The mass number is 138. Here, let's go to the next one. What is the mass number equal to? Yeah, number of protons plus the number of neutrons, which is 18. Okay, here we have 82 protons plus the number of neutrons should equal. So that means this has got to be 124. 124 plus 82 should give us 206. Is that correct? Okay. And then this is 30 plus number of neutrons we don't know, but we do have the mass number here. Remember? It would be 66. So this has got to be 36. So that leaves us with this mass number here. So 56 plus blank gives us 138. 82. Good. All right, so let's do the nuclear symbol for the oxygen. So oxygen, Z is easy. Z goes down here, that is 8. And then A goes up here, 18. So this is called oxygen 18. I told you that ozone in the atmosphere is different than ozone ground level. Ozone at ground level has more oxygen 18 than the ozone in the ozone layer, which has less oxygen. Oxygen 18 is heavier. The most common one is oxygen 16. Okay, what is this lead? 206 over 82. And then the zinc, 66 over 30. And so this isotope is called barium 138. This isotope is called oxygen 18. And this would be lead 206. And so this is the composition. So we know the composition. We know a little bit about the structure, the nuclear atom. And so if we know the composition, we know the structure, can you predict the properties? Possibly. Well, we would like to be able to predict the properties. So I talked about the disproved features of Dalton's. Atoms have subatomic particles, so protons, neutrons, electrons. All atoms of an element are identical. That's false. Isotopes are atoms of the same element which have different masses. So, could you tell, you drank some deuterium this morning. Could you taste the difference between deuterium and hydrogen? No, couldn't. In fact, what's that? Great question. Would you die if you drank deuterium? No, you would die if you drank tritium. Would you die if you drank deuterium? That is a great question. Let me do a different profile for this one here. We need to do this. Okay. A lot of you have had the same. Would you die if you drank heavy water?
When we first arrived at St. Jude, it was just Claire and I.
Obviously, it's quite a problem.
It's not going to work here. Maybe let's take a break right now and we'll do this. We'll try to answer the question. Or has it been 15 minutes? Oh, I forgot to shut this off, the recording. All right, let me just get started again here. So there's a break here. So there's this channel called Periodic Videos. And he has a lot of videos, like, for example, heavy water, plutonium, chromium, helium, thorium, arsenic, titanium, gallium, nitrogen, chlorine, indium, thorium, cal, tin, lutetium, etc. And so we'll take a look. There's 3 heavy water videos, the original one, and then this is heavy water part 1. Heavy water part 1 talks a little bit about the history. There's some kind of military mission in World War II, in which they set out to destroy heavy water plants. And it was deemed successful because there are no fatalities, no injuries in this. But we're going to heavy water part 2. I don't know what's with the audio. I think the audio is coming just out of the projector. Let me see if I can change the audio too. The audio was coming from the room last week, but this time it's not. Oh, this isn't the video I wanted. Sorry. I want heavy water part 2. Can you hear that okay? All right, we'll try this. Let me back it up. They call, there's different forms of heavy water. D2O is one of them. D2O, I used to have a bottle of D2O. And it looks just like water, probably tastes just like water, reacts just like water, is just heavier than normal water. Yeah, just by a small amount. And that small amount makes it difficult to separate heavy water from lighter water. Okay. Well, yeah, except it's such a small difference that it stays suspended. If you're looking at the ocean, yeah, if you look at the water on the ocean floor, it'll be more rich in heavy water versus the ocean at the top. It's the gravitational fractionation. But if you have a bottle of this stuff, and people use this, it's not just for nuclear reactions. I used to use it because regular water has some magnetic properties that are different than heavy water. So heavy water, there are some other properties. Magnetic properties are physical properties. They're a little bit different. So I used to use it because it wouldn't interfere magnetically with some other water. It's expensive though. So you wouldn't want to drink it just based on the price alone. But let's see.
Honestly, it's quite a problem. How do you make D2O? Because normally the deuterium in water is diluted by a factor of 7,000, which for chemists is really pretty dumb. The best way of making D2O is by and it makes economic sense to generate hydrogen for making ammonia and fertilizers by electrolyzing water. And if you electrolyze water, you find that the H2O reacts a little bit faster than the D2O. So if you go on electrolyzing more and more water, keeping what's left, and then doing several stages of electrolysis, you can gradually concentrate more and more of the D2O till eventually it's really pure. This process was carried out in a fairly remote power station in central Norway, in a region called Telemark. And one of the main uses of D2O in the early stages of nuclear science was for making nuclear reactors, nuclear powers. And during the Second World War, the British and the Americans were terrified that Germany, who occupied Norway at that time, might get hold of the D2O and start nuclear research. And in one of the best raids of the whole Second World War, 6 Norwegians attacked the power station, destroyed the heavy water apparatus, and retreated. And the reason it was so successful is that nobody was injured and nobody was killed. So they got into the place, blew it up, and escaped without anybody being injured. And in fact, the German general that investigated thought it was one of the most magnificent military feats he'd ever seen. There's another story that before the Germans invaded Norway, that the supply of heavy water, 2 cans, a few gallons, was smuggled out to Newcastle, and it was so valuable, it is said that it was built under King George VI's bed at night, so it should be safe before it was then transported to America. Is that true? Well, this is the legend, and the story is that when it was flown to America in an unheated plane, the water froze, so when the people took it off, it sounded as if the cans were empty, and they got really worried that they were empty. D2O has a number of applications, but its real use is in a technique called nuclear magnetic resonance. We've shown it on our video about tea, how you can use it to analyze molecules. And nuclear magnetic resonance is very sensitive to hydrogen atoms. So if you want to study some sort of molecules dissolved in water, if you use ordinary water, the hydrogen atoms in the water have such a strong signal that you can't study the dissolved molecules at all. So instead you use D2O, which do not respond to the same frequencies as the hydrogen, and so you get my spectrum. People watching will have 2 questions. What does heavy water taste like, and what will happen to me if I drink it? But I never tasted D2O. I suspect that it will taste really quite similar to H2O, though it's difficult to predict because sometimes things taste quite different. But water doesn't really taste anyway. You usually taste what's dissolved in the water, salts or whatever. There is a strong body of opinion that D2O is quite poisonous. And the reason why it's poisonous is because in your body you have all sorts of molecules that have hydrogen bonded, particularly to oxygen. And these bonds break as part of the various chemical processes in your body. Deuterium oxygen bonds are slightly stronger than hydrogen oxygen bonds. And therefore, if you start changing your body for the chemicals in your body from hydrogen to deuterium, these bonds will break more slowly. And so various processes in your body are likely to slow that down. If they slow down, they may completely stop.
Well, I was always told that you can kill someone by making a cup of tea with D2O, because what it does is there's a difference between the way that hydrogen reacts and deuterium reacts in the body. So it can replace hydrogen in the body, and obviously it's everywhere. It's in all the water, it's in the enzymes that
under which I've never been able to verify that the argon lab in the United States, just outside Chicago, at one time had a butylated dog, which had been brought up as of D2O. But I think this is probably just an urban myth and it never happened. There's also a suggestion that if you dilute your whiskey with D2O rather than H2O, then you might not get so dizzy when you drink too much. But you might be dead, so it's not something that one should try. And anyway, it's far too expensive.
All right, does that answer the question?
So it can't be.
Well, they're hypothesizing it could be because the bond is a little bit stronger with deuterium and oxygen. And there's lots of hydrogen and oxygen bonds, so it's going to react a little bit differently. But if it slows down, is that going to kill you? And how much slower is it going to be? Those kinds of issues. But I don't know if you want to experiment with it. But this channel is pretty interesting. It has a lot of videos like that. So I recommend it. Periodic elements. What we say is essentially, we drink D2O. We just don't drink very much. The concentration of D2O in water is pretty small. Atomic mass, we'll talk a little bit about this. I asked you, how is the AMU defined, or the atomic mass unit defined? And this is the definition here. Just read that definition, and can you explain it to me? Yeah. Right. And what does that say below it? These three lines, I don't know, I think that got moved here. I think it's supposed to be here. Now that seems to make more sense. Yeah. Can you take a carbon-12 atom and divide it into 12 equal pieces? Is that possible? No. And so normally what we do is we define it, I like to define it a little bit differently. 1U isn't really defined, but 12U is. So 12U is defined as the mass of a single carbon-12 atom. The carbon-12 atom contains 6 protons, 6 neutrons, and 6 electrons. So that would be it. And this would be 12U. And so if you could divide the carbon-12 into 12 equal pieces, which you can't, that would be 1U. So there is no definition. What weighs exactly 1U? Nothing. And so the common question is, what weighs exactly 1U? The answer is nothing weighs exactly.
So where do you come up with that measurement from?
You take a carbon-12 atom, and that's what you use to calibrate your balance.
Why do you choose carbon-12?
Why choose? That's a good question too. This is the new one. This is like post-1950s. The old one is like pre-1950s. The old definition of U was a little bit different. The old definition of the U is that 1 oxygen 16 is defined as 16U. Now, if you define an oxygen 16 as 16U, does that still make carbon exactly 12U? No. No, and so the mass of carbon-12 is no longer 12U. It's just slightly off. And let's see, I think all of you took exam 1, correct? Nobody missed it. Yeah. But don't talk about it just quite yet. But the definitions have changed. Like so, the periodic table has something called the average mass of all the isotopes, and that's a black number underneath the element. Those have changed. Those have changed. So if you look at an old periodic tables mismatch with the new periodic table because the way we define U. Those are the masses of U. And so the numbers are off a little bit. So don't use the old tables. Your calculations can be off.
Is 1999 still false?
No, that's good. 1999 is no problem. That's defined based on carbon 12. In the old one, they chose oxygen 16. So why didn't they just stick with it? Why didn't they just keep... The reason they didn't stick with it is because oxygen normally is a gas, and working with gases is more hassle. But oxygen is plentiful and it's free. But you're dealing with a mixture of oxygen. You have in air, you have oxygen 16, 17, 18. Now, oxygen also likes to form diatomic molecules. So it's just more hassle. You just have to deal with gases. Whereas carbon is a little easier. You get a piece of graphite. Graphite's cheap. Air is cheap. Well, both of those definitions have costs going for it. But the carbon 12 is locked up in the solid crystal, and so but we have lasers. You can just laser ablate, and so you hit it with a laser on the surface, and then vaporize some of the atoms, and then you can weigh those atoms individually. And so we can weigh these, and then you have what we call how do you weigh atoms? We don't use normal balance. Do you know how you weigh atoms? What kind of instrument you use? And so this would be the calibration standard. You calibrate your instrument such that carbon 12 is exactly 12U. And we can weigh single atoms using a mass spectrometer. And so we need to calibrate our mass spectrometer such that carbon 12 is reading correctly. Used to be you'd calibrate your mass spectrometer using oxygen 16, but that's not the case anymore. Maybe somebody will change it in the future. How about the kilogram? How do you, what's the standard or what's the... Yeah, but how's the kilogram defined? Yeah, a block of metal in a bunch of jars, right? That's the old definition. Do you know the new definition of the kilogram? That's what it's supposed to equal, but then how do you define 2.2 pounds? In other words, I want to calibrate it. Let's say you have a bathroom scale at home, it's reading pounds. How do you know it's reading the correct number of pounds? So if you put 100 pounds on the bathroom scale, and it's reading 100 pounds, is it really 100 pounds? It might be. We need to calibrate it first. Now, if you calibrate it, you have to have an object that weighs exactly 100 pounds. Is there an object that weighs exactly 100 pounds? Okay, is there an object that weighs exactly 1 pound? Tell me what weighs exactly 1 pound by definition. A block in a bunch of jars, a block of lead or something maybe, or in a bunch of jars? That's not it. You know how it was defined, how pound was defined? Maybe, actually I don't know. I don't know. Maybe there was a rock and somebody said, oh, this is a very valuable, precious rock. I'm going to call this 1 pound. This rock is 1 pound. And then they have it. Now, they probably kept it in a cave or something, a rock in a cave not long ago. Yeah, but if it gets chipped, you're right. That screws everything up. You have to find a new rock that weighs exactly the same amount, and then you can calibrate it, right? Or you can define it based on physics. You know, a pound is a certain amount of force, per area, that kind of thing, or just a force, basically. A mass times force is gravity. And so you could define it based on physics. The new definition of the kilogram is defined based on physics. So it's more accessible. You don't have to go to the vault. It's locked. You can build the apparatus. You can build the apparatus for I think less than $20,000 or something like that. And then you can use that to do it.
When was the pound invented?
I don't know. That's an interesting question. When was the pound invented, and how was it defined? Then the same thing. How was the Fahrenheit invented, and how was it defined? And so originally, I thought there was a person named Fahrenheit who had a laboratory and walked outside, and it was the coldest day they'd ever experienced. So they called that zero. But it turns out that was wrong. That was just a guess. But it's defined.
Assuming that the metric system, of course, is our history, came up only that history is school. And so the history was derived from
I think it's like different, geographical regions. I mean, there are different units that eventually a lot of these other units were lost, and replaced by this. But I'm not sure of the origin, but yeah, it could be totally. Metric just seems more logical. I mean, why is, if you have 10 fingers, why is a dozen 12? Can somebody answer that for me? Why is a dozen defined as 12? I mean, did they used to have 6 fingers in ancient times on each hand, and then they can count a dozen? Yeah, the physics. You know what somebody told me? It has to do with baking. When they made the bread sheets or something, they could fit 6 in an oven or something like that, and so they called it half a dozen or 12 in an oven. But you think you just make it bigger or smaller, the bread. So, but does somebody know the definition of a dozen? Yeah, but where and how was it defined, and who defined it? Do you really care? Probably not. Yeah, this is some baker. I haven't cared enough to go look for it. But you need to know certain definitions. You need to know the definition for a kilogram, but the definition for kilograms changed, and actually the two masses don't match. So it brings up the question: if you buy a kilogram of gold by the old definition versus a kilogram of gold by the new definition, did you lose some gold or did you gain some gold?
Is it like more?
You lost or gained, but it's such a small amount. People don't worry about it, I guess. It's so close, but it isn't exactly the same.
Doesn't came from the cycles of the moon for one cycle of the sun.
Oh, was it? Okay. Thanks. Cycles of the moon. I had no idea.
Yeah, came from like 12 cycles of the moon to one cycle of the sun.
Okay. Then that makes sense. The frequency. That totally makes sense. And then it translated. This is not a dozen here, though. This is what do we call that number again?
Isotope.
The isotope number, but more specifically, we call it not the atomic number, the mass number. So does that mean carbon-13 weighs exactly 13U? No, it's not the case. This is the only thing that weighs exact, and it's carbon-12. You need to know the definition of atomic mass unit, and this is it. So this definition you need to know. Who came up with this? I don't know, some group of chemists, physicists came up with this. You don't need to know who came up with it.
Does it matter which one we write down? Say that's on an exam. Does it matter which one we write down? 12C equals 12U, or does it matter like 1 with 112?
It doesn't matter. You could write 1U is equal to 112, but I always do this definition. I always do this definition because we use that definition for something else. We'll talk about what we use it for. So I never do the 112 of carbon. Conceptually, it's difficult to visualize.
Yeah.
Slicing a carbon into 12 equal pieces just doesn't work. So I only use this definition here. So this is the output from a mass spectrometer. When we weigh atoms in a mass spectrometer, it's like this here. And you calibrate it. So over here is 12, and you feed carbon-12 atoms in here, and they all land here, and then you punch this into your computer. This is exactly 12. And then we'll have neon. It turns out neon has 3 different isotopes. You can see them here. Neon has one isotope that weighs around 20, another one that weighs around 21, and another one that weighs 22. These are approximate. These aren't exact here. We can get more precision if we look at the digits in more depth.
Can we have like a number of isotopes?
Not an infinite number. There's only a certain number of isotopes that we have. For neon, there are more isotopes than this, but the other isotopes are man-made radioactive isotopes. So there's like neon 19 over here and 1 at 23, but those aren't stable. These are the stable isotopes of neon. So if you have a neon lamp, your neon lamp, all the neons aren't exactly the same in a neon lamp. Some are heavier and some are lighter. These are the actual masses, not the mass numbers. But the masses and the mass numbers roughly correlate with one another. Why? The mass number, which is not a mass, and the actual mass correlate with one another roughly. Why?
Are they very
Yes. Why are they very generally similar to one another?
The average of all the isotopes.
Well, no, the mass number is the number of protons and neutrons. The protons weigh about how much? The neutrons weigh about how much? 1. And electrons don't weigh much. And so most of the mass is concentrated in the nucleus. So if I have an isotope of neon that weighs about 20 U, then that means that's about 20 U's worth of protons and neutrons, and electrons we can kind of ignore. So this would be neon 20. This would be neon 21, this would be neon 22. So the mass number and the actual mass are somewhat correlated, but not exactly the same. And so with the mass spectrum gotten from the mass spectrometer, so let's back up here. So we take a mass spectrometer, which is the instrument, and we feed the element in there, and then we end up with a mass spectrum. From the mass spectrum, what you can get are the number of isotopes, the mass of the isotopes, and we can get what we call the relative abundance or the percent abundance of the isotope. The percent abundance is we just add up the total. And so these, if we add up the total here, this is percent abundance actually. So they add up the total, that makes 100%, and then they just look at each of these in terms of their percentages. Let's just look at how mass spectrometer works. Let me see if they show that on the next slide here. They don't. Oh, this is wrong.
Okay, what we have here is a mass spectrometer.
All right, this doesn't
It's
have
made of
audio.
lots of different stages, and some of them use.
If you have a gaseous sample, then it's fine. You just enter the gaseous sample through here. If you don't have gaseous, let's say you have a liquid or solid sample, then what you need to do is you need to vaporize the sample. It's converted into gas. So you could use a hot filament or a laser, or you could shoot particles at it. Particles like electrons or small molecules, you could shoot at it. And what you do is you're going to vaporize the atoms. And then what you do next is this electron gun here. Electron gun is a cathode ray. You know what were cathode rays again? A beam of what? Beam of electrons. And so you have a cathode ray here, shooting electrons here. You charge the atoms. Once the atoms acquire a charge, then they'll be attracted. So, for example, you can accelerate them towards a plate, either positive plate or negative plate. See, if they're negatively charged, they'll be attracted to a positive plate. Maybe it's positive. They get accelerated. And then they get deflected by a magnet. The magnet's going to deflect. Now, the heavier ones are hard to deflect. The light ones are easy to deflect. And so the lighter isotopes hit over here, the heavier isotopes hit over here. You have a detector, you put it on a computer, and you generate a mass spectrum. And so what this does is, based on the magnet, it will separate out the isotopes based on their mass. And then by the number of strikes on the detector, let's say most of them strike here, then we'll build up the peak. And the larger the peak, the greater the abundance. So that gives us a mass spectrum.
Electric field, some they use magnetic field, and
I
some
don't
they use
know.
both.
Velocity selector is weird.
Become ionized. Normally, you knock out one electron, making it
In this case,
velocity. So if we
the
apply
velocity
Fleming's
selector, they're
left-hand rule,
trying to make them go the
we can
same
find that
speed,
we need the
I
magnet
suspect. But in a regular mass
is
spectrometer,
the potential difference between those two
we
plates
just have a
divided by
magnetic field there.
the
And
distance
so this
between
is
those
for
plates, d.
deflection.
Now note
And
that
so we
this
don't
voltage
really
is
say
different from the
velocity
voltage.
selector, we say it deflects it. Let me get a different mass spectrometer video here.
Welcome to subtopic 2.2, the mass spectrometer. The mass spectrometer is a vital instrument in many kinds of chemical analysis. But how does it work? And how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then, it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer,
Let's just see them.
5 stages.
5 stages.
First, the sample is vaporized. Then it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrum.
Yeah, cathode ray tube. The cathode ray tube was instrumental in determining the mass of an electron. The mass of an electron is very small, like 2,000 times less. And so using some physics, what they did was they have the beam of electrons, and then they put a magnet there. And what happens when the beam experiences a magnetic field? It gets deflected. And based on the angle of deflection, they got the charge to mass ratio. once they have the charge to mass ratio, then they have two unknowns. The charge on the electron was unknown. I told you the charge is -1, but that's -1 fundamental unit of charge. There's actual units of charge called coulombs, so they didn't know how many coulombs the electron was. So there are two unknowns. The charge on the electron was unknown, and the mass on the electron was unknown. And so when you have two unknowns, what do you need? You need one more equation. Oh, you know what the one more equation is? Very famous equation that came from a very famous experiment. And at Griffith Observatory, you can see one of these things. It's called the Millikan oil drop experiment, where what Millikan did was he vaporized oil droplets, just so that he got fine oil drops, not atoms like we have here. And then had a source of what we call ionization source, and attached electrons to those oil drops, and then measured how fast they fell. Some didn't even fall in an electric field. He was able to get the charge on the electron. Once they had the charge on the electron, they were able to get the rest. And so there was one more critical experiment in the electron, and that was the Millikan. So it wasn't just J.J. Thomson. J.J. Thomson was critical for the discovery, but there's more to it. Let's see if there's anything else here. Oh yeah, the deflection part comes from the magnet, and we get the charge to mass or the mass to charge ratio. I like to do whatever. And so the two unknowns here, but we can get one of them if we have carbon-12. If we have carbon-12 here, where does it strike? It strikes exactly 12U. And so we can calibrate our mass spectrometer by introducing carbon-12. When carbon-12 hits the detector, then we set the computer. That's exactly 12U. And then we can figure out the rest based on physics. No, these are atoms. You can in the cathode ray tube, it was electrons. In a mass spectrometer, it's atoms or molecules. You introduce molecules into mass spectrometer. So we end up with something called the mass spectrum, and it depends on how many strikes. So let's take a look at this here. I'm going to speed it back up, maybe.
And then detected.
So they have one isotope.
We can record its mass charge ratio. If
you can see it building up there.
Size
This is a weird one. And we end up with this. This is a mass spectrum.
Was the rubidium 85
Here we just see two isotopes. So from the mass spectrum,
while the rest was the rubidium 87 isotope. If we multiply the percentages times their mass
in fact, these masses are compiled in tables. So if we look at rubidium, we'll go there in a minute.
then average that over 100 atoms, we'll find the average atomic mass of rubidium.
If we knew the theory well enough, then
let's try the reverse. Let's calculate the relative abundance
because what happened here is
boron.
Let me pause it here. How do you know it's all because there were no other peaks? And so this is just a chunk of rubidium. Rubidium is metal. This is just a chunk of rubidium, and then they vaporized a lot of atoms, and that's all they saw.
Okay.
If there were other peaks, then there'd be more isotopes. Only two.
How do you guys different like sources are saying?
Oh, okay, different sources. Yeah, that's important. What if the rubidium came from the moon? What if the rubidium came from the moon? You would probably expect a slightly different percentage here. It depends on the source. So, for example, if I took my oxygen from the ozone, in the ozone layer, and then I took my oxygen down here from Earth on the surface, are they going to have the same distribution of isotopes? No, it turns out the ozone is going to have a bigger peak at the lighter ones and a smaller peak at the heavier ones. Whereas down low on Earth, we'll expect the heavier ones to be more abundant. And that's just because it weighs more. Does that make sense? And so what we do here is we just average everything. And so it depends, yeah, it varies slightly depending on where you get it from. And so what you'll do is you'll measure a whole bunch of samples and just take the averages. But you'll definitely see some fluctuations there. Now, if the fluctuations are very significant, then you can use that to trace the origin of certain things. And so this is a very important topic in science called isotopic fractionation. There are people who are really studying how, this is called the fraction of the isotope, how isotopic fractionation impacts, impacts things. And so this is a major field of study. What we do is we just take the average of a whole bunch of samples, and that's what you see here. So this rubidium is not just one sample. This rubidium, the 7723, is a bunch of different samples, and then averaged. Now, the differences might be so significant we wouldn't want to average them. And then that tells you some information that would be quite important. And so,
On the black, they walk the red, and after the green, green for the eyes just the contrast just right over
you have to look at some of the. You're talking about the ones in the parentheses, right here. The ones in the parentheses are very difficult to measure because they're so reactive, they don't last very long. And so it's hard to weigh them. And so that's why there's a lot of uncertainty in the weights. So isotopic fractionation is used in lots of fields, geology, just in science in general. So here's a paper here. Isotopic fractionation of oxygen by respiring marine organisms. So when they inhale the oxygen, what is the ratio? When they exhale, what is the ratio? What gets incorporated in certain things or whatever. And so when we read a scientific paper like this, we probably don't want to read the whole thing. Typically what we do is we just read the abstract. So I don't know what they're doing in this particular paper. This is something that I'm not that familiar with. But anyway, we measured the respiratory isotope effect for 7 represented unicellular marine organisms, bacterium, et cetera, they exhibit values in the range of 14 to 26%. We also measured the 3 metazoans, whatever, at 17 to 25%. So what they're doing is they're looking for differences, and they're seeing if they're significant, and if they can be correlated with certain properties or whatever. And so here, getting down to it here, supports the hypothesis. Okay, marine organisms, it depends on how deep you are, right? How much oxygen, the heavier ones you have versus lighter ones. And so here, oxygen 18 is one of the heavier ones. And so the large value and high variability of these limits the usefulness. So maybe it's not so good is what they're saying. And so you can't really tell much. But they were looking at the oxygen 18. They were trying to use that as a tracer because, the heavier oxygens are going to sink deeper, just like the heavier water should sink deeper in the ocean, right? The heavier oxygen should sink deeper, and so maybe that gives us a way to trace the depth depending on how much oxygen, let's say you catch a fish or something, how much oxygen 18 might be able to tell you how deep it was in the ocean. And so that's what they're looking at. And if they can get a decent correlation, then maybe they can use that. They certainly can use it for altitude, but altitude is tens of thousands of feet, you know. Maybe and deep sea creatures will have much richer oxygen 18. Uh-huh. Tritium is radioactive, so it's really not. It's deuterium for sure. D2, yeah. It's going to be just because the weight difference isn't so big. You know, a regular water molecule weighs 16 U, and then the heavier one just weighs 20 U. So 16 versus 20 is not a huge difference in mass. And so it makes it. So this is they're proposing maybe to use it as a tracer, but they found it of limited usefulness. And so this is something the geologists do and others, and so they're thinking maybe for a biological system it might be good. It still might be. It depends on how sensitive the measurements are and that kind of stuff. And so we can easily measure this type of stuff using, what was this instrument called that generated this thing? The way that we measure the masses of...
Mass spectrometer?
Yeah, mass spectrometer. Using mass spectrometer. Mass spectrometers aren't that expensive. Many labs can afford them. All right, let's look at this example. The natural distribution of the isotopes of boron is 19.9% boron 10 at a mass. Okay, now they're giving us the mass. How many sig figs is this one? This shows you how precise the mass spectrometer is. How many sig figs did the mass spectrometer spit out? More.
Oh, sorry,
9 sig figs. Incredibly precise. 9 sig figs. And 80.1% boron 11. And the boron 11 weighs that much. Okay, now it's asking you to calculate the atomic mass. When we say atomic mass, this is what we call the average atomic mass of all the isotopes. It's a weighted average. And so let's talk about the atomic mass here. What, you know, let me tell you, I'll just do it to 2 sig figs. The lightest water molecule weighs 16 U. And the heaviest water molecule, which is D2O, tritium's heavier. But tritium, you don't want to drink tritium water because it's radioactive. And so the heaviest you'd want to drink would be D2O, which weighs 20 U. Wait, 18, heaviest, lightest 16, 4. But what we want is, what's the average water molecule weight? You'd say the average is 18, but you know the average is not 18.
26.
19. The average is 16, roughly 16. Do you know why that is?
It's much more, it's too much.
Yeah, right. There's so little D2O that it's essentially pure H2O almost. There's so little D2O that the average is about 16. This is called a weighted average. You'd think the average would be 18, right in the middle, but it's not. It would be 18 if it was a 50-50 mix. right? It's a weighted average. This is like saying, okay, let's say you have 1,000 people. If you have 1,000 people, and each of these weighs 100 pounds, we'll say roughly, and then you have one person that weighs 50 pounds, then what's the average? Would you say the average is 75 pounds, right in the middle? No, you'd say the average is close to 100 pounds, right? And so this would be the weighted average. The average is going to be about 100 pounds. And so this is the same thing. If you look at all the water molecules weigh 16 U, and then once in a while you get one that weighs 20 U, and therefore the average is going to be about 16 U. Well, we do the same thing. So most of the boron, 80% of the boron weighs 11, and only 20% of the boron weighs 10. So the average is going to be closer to 11 or closer to 10?
11.
The average is going to be closer to 11. And so what is it? It's going to be about 10.8. 10.8. Because we're 80% of the way to 11. But what we're going to do is we're going to put that into a mathematical equation. And so the average atomic mass, which we just labeled atomic mass. When somebody says atomic mass, they're talking about the average, is equal to, I do the fractional abundance or the decimal abundance. Fractional or decimal abundance. Of isotope 1 times the mass of isotope 1. Plus the fractional or decimal abundance of isotope 2 times the mass of isotope 2. Plus however many isotopes you have, dot, dot, dot. So here they're doing the decimal abundance. They take 19.9% and convert it to decimal. I would just do 19.9 out of 100. I would have done that. Times the mass. The units here are U. And then they do the decimal abundance of isotope 2 times the mass of isotope 2, and they get this. Then they combine the sum. Instead of 10.8 U. Yeah, sum of these. And so the average boron atom weighs, or in other words, boron has an average mass of 10.81. So let's take a look at lithium. And I would do here, it's 7.59%, so it depends on how many. I just do fractional, 7.59 out of 100. This fraction weighs 6.01. 5.124 U plus 92.41 out of 100 weighs and at 7.01 60041 U. This is going to give us the average atomic mass. And the average is 6.94. Now, this is the average, but there are no atoms of lithium that weighs this amount. The lithiums are either going to weigh this or this, but there are none that weigh 6.94. That's just the average. We can compile this data. Oh, I'll come back to it. All right, go ahead. Into something called a table of isotopes. So a table of isotopes compiles all the mass spec data.
What is it combined?
All the mass spec data. We could visualize it using graphs. Scientists love graphs like this. These are all the isotopes. You said, are there an infinite number? No, but there are a lot. So if you look at carbon, which is element number 6 here, there are how many known isotopes? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 known isotopes. Most of those are radioactive. There are only 2 that are non-radioactive. Carbon 12 and carbon 14. Carbon 14 is radioactive, etc. So we can pick these different elements here and then figure out what we observe. So if we go to calcium, how many isotopes are there for calcium? 1, 2, 3, 4, 5, 6, 7, 8, 9. A lot of isotopes. We also have this style of table. So we just looked at boron. We found there are 2 isotopes of boron, boron 10 and boron 11, at 19.9% and 80.1%. This gives us the composition. Here are the atomic masses for 106 states. And then the average mass. The average mass is sometimes included in the table and sometimes not included. In this case, it's not included, but we did go over here. The average atomic mass is included on the table. So I can go to boron over here. But I don't know how many isotopes there are. When I look at this entry, I just know the average mass of all the isotopes is 10.81. In this case, 10.811. But how many isotopes there are and what the mass of those individual isotopes are, I don't know. Same thing with carbon. Look at the average atomic mass of carbon is 12.011. What weighs exactly 12U? Carbon 12. And the other isotope of carbon 12 here. Carbon 12 weighs exactly 12U. They don't need this 0.0. I don't know why they put it there. But there's one other isotope of carbon, that's carbon 13. Carbon 13 weighs 13.00335 or 826U. What's the average of 12 and 13? 12, what should be 12 and a half, but what is the average? The average is 12.01, which means that it must be mostly carbon 12 or carbon 13. It's got to be mostly carbon 12, and that's what we see here. It's 98.9% carbon 12, 1.1% carbon 13.
Is it only naturally occurring isotopes?
Yeah, all the radioactive ones, no. Those are usually synthesized using nuclear reactions. And so there are a lot more isotopes of carbon. In fact, a lot more isotopes of carbon, but in addition, carbon 14 is the most common radioactive one, but there are other ones. How many isotopes are there? These are naturally occurring, not the radioactive ones. And naturally occurring means you can just find these in nature. So if you take a sample of oxygen, how many different isotopes of oxygen are there? 3. What are they? 16, 17. Yeah. They all have the same number of protons. What's different are the number of neutrons. 8, 9, and 10 neutrons. Well, which one's the heaviest? 18. Oxygen 18, and it weighs about 18. You see that? 17.99. The lightest, 16, and it weighs about 16. It's because the mass number and the actual mass are close numerically. Yeah. 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 If we could round it, then if we ignore the electron. Now, which one's the most abundant? By far, 16. So the weighted average is going to be very close to 16. And it's 16.00 or 15.999. Uh-huh. Yeah, electrons don't weigh much. But there's one other problem with this chart. We'll talk about it later. Because think about this. If the proton weighs 1.0 and the neutron weighs 1.0 and the electron weighs something, but not much, why is the mass less than 18? It should be more than 18. No, it's rounded down, so the actual mass is heavier. And so the question is, why the mass should be greater than 18? Why is it less than 18? Why it's less than 18 is called the mass defect. It's not right. It should be greater. And the reason is because some of the mass of the atom was converted into what we call the nuclear binding energy. And the nuclear binding energy holds the nucleus together. It's the energy that's brought down.
And it was also weight?
It's part of the mass. Yeah. This is the what they call for the power of the nucleus. The power of the nucleus is wrapped up in the nuclear binding energy. There's a lot of energy stored there. And so this is what makes nuclear bombs so much more destructive than chemical bombs. Like TNT is nothing compared to a nuclear explosion. And so that's very frightening. Not only that, but nuclear stuff is dealing with unstable radioactive things. Anything like for example, Fukushima. Fukushima was a huge disaster. They generated so much nuclear pollution there that they ran out of space to store it. Did you hear about this? Did I already talk about this? Yeah, they said they're running out of space, so what they proposed. You know what the proposal was? You dump it in the ocean. You're right, because the solution to pollution is dilution. That's what I learned in elementary school. The solution to pollution is dilution. But so they tried this. They tried diluting. They used to dump DDT, which is a pesticide, out by the Channel Islands there. That wreak havoc on the brown pelicans. And they dump mercury in the ocean, but mercury has something called a biological magnification. Have you heard of that? And so some people are saying, oh, don't worry about the mercury dispersion. There's a lot of mercury that blows in the dust from the east, basically. And so a lot of the dust that hits the U.S. is contaminated with mercury from pollution sources in Asia. And but the solution to pollution is not always dilution, so they stopped. I don't think they teach that anymore. Do they teach that anymore? Because it's clearly wrong. It's totally wrong. But people are still using it because people are still saying, well, we can dump the nuclear pollution in some of these radioactive isotopes in the ocean because it's just going to dilute. But people are still thinking that's acceptable. So the company that runs it wants to do it, and then the government approved it, and so they sort of started dumping it into the ocean. I disagree with that. How many isotopes are there for chlorine? 2. One weighs about 35. The other weighs about 37. Now, what's the average? So if we go to chlorine, I can find the average here. It's 35.5. So this is another way of visualizing. If I only have two isotopes, one weighs 35, the other weighs 37 over here. Let's say it's 50-50. What would the average be? 36. But it's not 50-50. It's 35.5. If it's 35.5, that tells me it's 75% chlorine 35 and 25%. Do you see that? Based on where it is in the spectrum. And so that's what it is. It's 75% 35, 25% 37. So that's kind of the weighted average visualized. So we have our table of isotopes here. Actually, I could have used this on page. But there's some interesting stuff. One of the interesting things is fluorine. How many natural isotopes are there for fluorine? One. Only one. So all fluorine atoms are identical, and they weigh the same amount. So the average is the same as this. What's the average mass of fluorine? It's the same as the mass of fluorine-19, which is 18.998. And so that's what we call a single isotope. What else has just a single isotope? Beryllium. Yeah, Be. 100% beryllium-9. Fluorine, 100%. There's another one, phosphorus. Phosphorus is more important for bio, I think. Phosphorus is an important element in biology. But that's also 100% natural abundant. I'm not sure why they didn't put it on the table here. Sulfur has 4 different isotopes. So if we have more isotopes, we just add more terms. So here's the decimal abundance, 94.93% this, 0.76% this, 4.29% this, and 0.2% that. We just add it up. So the average of all 4 of these is 32. So it's closest to this one. This one here. This one has the highest abundance. So it's going to be close to 32. So what we want to do is we want to be able to correlate the composition. We know the composition, and you know the structure. What's the structure? Well, the structure, the number of protons and the number of neutrons, that's what we call the composition. Like how many protons, how many neutrons, how many electrons. Composition. And we know the structure. What's the structure of the atom? Plum pudding? Or nuclear? Nuclear. That's the structure. Okay, now we need to correlate it with properties. So when we do that, we have to measure a lot of properties and see how they correlate. And so Mendeleev was the first person, and Meyer, actually. They did it independently. They didn't work together. Mendeleev and Meyer arranged elements based on atomic masses. Found that certain properties repeat at regular intervals. Arrangements were not perfect. There are errors in atomic masses, strict ordering property with the atomic number Z. So we have the periodic table. The periodic table is based on observations of properties. So what they do is they group the elements based on properties. So if you look at Mendeleev's original table, it's similar to this. This is the modern periodic table here. Although the modern periodic table is about element 120. These ones, I don't know what the date is. It's 2009, maybe. Something. So these are based on properties. So what we need to do is we need to correlate. So for example, if I have 1 proton, it's here. If I have 2 protons, it's here. Totally different properties. And then if I have 3 protons, we're back here. 4 protons here, 5 protons, etc. And so what you do is you start to look for a pattern in the composition. The structure is all the same because it's a nuclear atom. And so do you see a pattern in the composition? So if I said this, would you have been able to predict this? So if I have 1 proton and then we go to 3 protons is very similar. And then we go to 11 protons. Well, tell me the next one that's going to be similar. How many protons do it have? Can you predict that? Do you see a pattern there? It's 19. It looks like 8, huh? And then, but then this one throws it off. This one goes to 37. So people look for number patterns. And the number patterns that they see, they're some critical numbers. 2, 8, 18. Do you see that pattern? 2, 8, 18? It goes 2, 8, 8, 18, 18, 18. And then the big one. The big one is, okay, this is 2 plus 2 plus 8 plus 8 plus 18 plus 18 plus a lot. But do you see that pattern? And so people start looking for patterns like that and then try to figure it out. Yeah, but sometimes when the patterns don't hold, you know, when a pattern holds and it's very predictable, we call it a law. But if a pattern is not so predictable and doesn't hold as well, we don't call it a law. Do you know what we call it? We don't call it a theory because the theory is the best. We call it a rule. Rules, you know, you can break rules. It's not a big deal, you know, versus breaking a law is more consequential. But do you see any kind of patterns there? Can you predict base? Why is adding 2 protons is going to be similar? And why is adding 8 protons is going to be similar? And why do it when we add 1 proton, it's quite a bit different? You know, going from hydrogen to helium is just 1 more proton difference, and it makes a huge difference. Yeah, and the reason is because we don't understand structure well enough. And it has to do with the shell. But, okay, so at this point, no, it's too difficult to correlate composition, structure, and properties. But what we have here is the periodic table, which is correlating did I keep the recording? Yeah, which is correlating the properties quite well. And then we have the, in the periodic table, we have 3 entries here. Number of protons, the atomic number, the symbol, and what's the atomic mass? That's the average of all the naturally occurring isotopes. So sodium, I don't know. Do you know how many isotopes sodium has? I don't. But you do know the average. It might have just 1 isotope. Does sodium have 1 isotope or multiple? Let's see if we can see it here. It's not here. We'd have to get a bigger table to see. Do you know sodium has only 1 isotope? But you can't tell looking at the periodic table. And so in the periodic table, we have the rows. The rows are called periods. And the periods, the properties vary gradually across the period. And then we have the columns. The columns are called groups or chemical families. And those, the properties are very similar. Okay. And then we have the different parts of the main group versus the main group or the representative versus the transition group or the transition elements. We have the metals, the non-metals, the metal ways. So let's take a look at those right now here in the periodic table, and then I'll be done with chapter 5. These ones in this block here and these ones in this block here, both of these are called the main group elements. This is where the 8 pattern comes in. The 8 pattern comes in from the main group because as you go across, there are 8 elements in that. And then these ones are the transition. There are 10 elements across here in the transition elements. And then we have the ones down here, the lanthanides and the actinides down here. These are the ones you're supposed to memorize, but, you know, I had some more in here. Like, we want potassium, calcium, and then scandium, titanium, Ti, vanadium. And then from zinc, we had gallium, germanium, arsenic, selenium, some extras in there. Below calcium is strontium. Strontium is an important element as well. Calcium, strontium, gallium. There's some additional ones. But we're going to come back to this. So what we're going to do is we're going to slowly build up a better understanding of the properties of the elements. We know the composition is different, but how can we predict? So if something had 30 protons, can you predict its properties? Maybe. Yeah. Okay. Let me talk. So we have this. We'll just finish off with this. Well, let's name these.
Lithium, sodium,
Beryllium has a bad reputation. You know, beryllium, like magnesium is lightweight metal, beryllium is lightweight metal. Beryllium is used in aerospace. Did I talk about beryllium? The machinist is very toxic. A lot of people die in the South Bay here from beryllium poisoning.
magnesium, calcium, barium,
I go calcium, strontium, barium.
chromium, nickel, zinc,
What's below zinc? You need to know this one. Cadmium and
gold,
silver. Zinc, cadmium, and silver are the fixed charge ones. All these are variable charge.
helium, boron, carbon, nitrogen, oxygen, fluorine, lithium, phosphate, bromine.
Wow, you guys already have those. That's good. Yeah, there's a periodic table song if you're interested.